While GPS is a useful technology for large-scale outdoor localization, GPS is unfit to locate and track in environments that are either GPS denied or require sub-meter precision. For example, users navigating through unknown buildings will not have the aid of GPS to localize, and autonomous vehicles will require sub-meter precision in order to avoid colliding with obstacles. As 5G millimeter wave networks continue to expand across the world, companies will need to include more services for end users other than just faster communication speeds. Millimeter wave networks provide location services for objects in a certain environment, similar to how minimaps in video games allow players to determine who and what are around them. A real-life minimap has many benefits. Autonomous vehicles will be able to reliably navigate in close proximity to obstacles, and people will be able to seamlessly find their way through indoor environments. To make such a system possible, we developed a hardware-independent localization and tracking system, which offers reliable and precise target positions for a network of passive, low-cost millimeter wave devices. We call this system Multistatic Networking with Millimeter Wave Radar Array for positioning, or MiNiMAP for short. This project uses a network of 3 millimeter wave radars manufactured by Texas Instruments to model any millimeter wave device. We collect raw ADC data from the millimeter wave radars in order to replicate the fundamental operation of any millimeter wave device. Therefore, MiNiMAP is a hardware-independent system. MiNiMAP solves the challenge of localizing with many low-cost devices by utilizing the network localization and navigation paradigm. We improve the target belief state through spatial cooperation with neighboring radars, and also through temporal cooperation via Bayesian filtering of target detections over time on each millimeter wave radar. Here we demonstrate how MiNiMAP processes backscattered signals from millimeter wave radars and transforms them into real-time target tracks in an indoor localization application. In the indoor environment, 2 mobile 5G users are represented by these encircled radars, and 1 5G base station is represented by this squared radar. As the target walks through the room, it is in close proximity to each of these neighboring millimeter wave radars. As we freeze the frame, we can see how the backscattered signals from each millimeter wave radar interact with the target. MiNiMAP employs synchronization and scheduling strategies to solve the interference problem, as well as leverage multipath information generated from other millimeter wave radars in the network. After MiNiMAP collects observations of the environment during a period of time, it transforms the time domain ADC data from the device into range, velocity, and angle of arrival detections. The 2 plots on the left of the figure show the backscattered signals, and the 2 plots on the right of the figure show the detections produced from the data. This happens on every millimeter wave radar at every time step. In the next few examples, we are only focusing on the perspective of device 1, where you will see how MiNiMAP makes the right 2 plots easier to interpret. Although MiNiMAP is capable of collecting detections of the true target 90% of the time, it also collects clutter detections from other objects in the room like the chairs and the walls. MiNiMAP employs 2 statistical signal processing techniques, peak grouping and background removal, to avoid tracking detections from stationary objects. Compared with before, there are much fewer red X's signifying detections from device 1 on any of the surrounding chairs or walls. However, there are still clutter detections from non-informative multipath. An ordinary system would not be able to differentiate these additional clutter detections from the true detections, but MiNiMAP employs an unscented Bernoulli filter to solve the data association problem and track the target. Here, you can see the effect of applying the filter to the detections produced by a single millimeter wave radar over a period of time. It tracks the target fairly well, but MiNiMAP can do better yet. By leveraging the advantages of spatial cooperation, MiNiMAP can accurately track the target's movement. Enabling networking of the 3 neighboring devices improves the quality of the target track. The fusion of the information MiNiMAP gathers from the network, together with an advanced tracking algorithm, outperforms the target's position estimates generated by just 1 radar's detection. Specifically, MiNiMAP's mean estimation error of the target's position for this test is 3 centimeters, while a single radar experiences only 5 centimeter accuracy. When a true detection of the target existed in this test, MiNiMAP produced an estimate 74% of the time, while a single millimeter wave radar produced an estimate 46% of the time. In conclusion, MiNiMAP can impact a variety of applications such as indoor navigation, autonomous vehicles, security systems, search and rescue, and patient monitoring. MiNiMAP is a system of millimeter wave scheduling and processing techniques that can be used on any passive, low-cost millimeter wave radar array to give precise positions and reliable tracks of close proximity targets.